Good morning, Albert.
Good
How are you?
morning.
Thank you. Today I coming early.
Yeah.
Thank you.
Okay. Uh, I have started a share screen, so I hope you can see the screen. Is that correct? Can you
Number
see?
12.
Can you see the screen?
Yes.
Good.
Yes.
Good. Good. Okay. Let's start. Today we are about the early Earth, the the beginning of us. First of all, formation. Just a bit of revision here. Um, The solar system is formed from a large rotating cloud of interstellar dust and gas, which called solar nebula. It's composed of mainly hydrogen and helium, but obviously we know that we have other elements here as well. So there are some other heavy elements, most likely ejected by a supernova some time ago. So about 4.5 GA giga annual years before us. So that is 4.5 billion years ago. The nebula began a contraction that might have been triggered by a shock wave from a nearby supernova. A shock wave could have made the nebula rotate as the clouds begin to accelerate the angular momentum, gravity, and inertia, flatten it into a disk perpendicular to its axis of rotation. Small perturbations due to collisions and angular momentum, other things, and then eventually created all of us. So let's go to a little bit more in more detail. The center nebula, which becomes our sun, uh, being lighter and with less angular momentum. So it's not rotating. Angular momentum means rotation. So it's not rotating as much. Therefore, it collapsed much quicker. The collapse is attracting each other, and therefore it is a compression. As it is a compression, therefore its temperature increase until the nuclear fusion of hydrogen into helium began. And when that began, then suddenly it becomes have a photo radiation energy rating out of it, and at that time it becomes a Tauri star, and then eventually the star evolve into the sun, enter into its main sequence. The outer of the nebula continue to rotate around this center, and then they also collate together to form our planets. Initially as a disk and then eventually becomes a planet. So successive layers of all these dust and debris are clumped together to form the planets. Each formed in this manner about 4.5 billion years ago, or 4.5 for GA, with the uncertainty of around 1%. So we can say it's about 4.50 to 4.58 billion years ago, something around that number. So, and the process of this take about 10 to 20 million years. When the star light up, our sun light up, the solar wind will blow off many of the gases close to it. So our inner planets will not have all the gas, whereas on the outer planet they will have more of the gas, and that's why our inner planet is mostly um, heavier elements, whereas the lighter elements are all located out in the outer planets because of this solar wind. The same process of this occur for all these other stars, so we can observe that in astronomy. We are now focusing on us. Last time we talked about the inner planets. We are the number 3, and then there's a belt, and then after that there are the giants. So we skip our Earth last time because we want to put more attention to it. So we are now looking at the Earth. The proto-Earth is mostly, this is a very difficult word, siderophy metals. What does it mean is elements which will bind to iron. So most of the elements which can bind to the iron will be one of the more abundant elements on Earth. Then it will cling together, and as they are denser, and therefore they will tend to sink in the middle. The so-called iron catastrophe resulted in a separation of the primitive mantle and the iron core, and then the iron core begin to form in around 10 million years, and then producing our current structure. And because we have a magnetic iron core at the middle, and therefore we have the magnetic field. Our magnetic field is the rotation of this molten iron plus all the other elements. The magnetic field in Earth has been changing all the time. We have flipped many times. So the flipping of the magnetic field will not cause catastrophic effects on Earth, which a lot of people say they will, but in fact they won't. The magnetic field is a consequence of the mainly iron in the middle of our Earth. Quite soon after this formation, the whole formation is called accretion. That means it is sticking all the other smaller derbies, which is formed from the supernova, and then attracting them towards Earth. It is attract towards Earth from the point of view of us. We saw these asteroids, comets smashing onto us. So we call this the heavy bombardment period. So at the very beginning, there will be a lot of these smaller objects which will be attracted by Earth's gravity, and therefore fly towards Earth. As that becomes the first 500 million years, is almost heavily bombarded by different asteroids, different rocks. Of course, when they hit on our atmosphere, it will melt, and some of them will hit on the rock, will hit on us so energetically that it actually melts. The oldest rock that we can find on Earth today is about 4 billion years old. But that is not the oldest thing. The oldest thing is actually an asteroid, which becomes a meteoroid, and then we collect on Earth. That will be older than us because it will be formed during the supernova. But for all the rocks formed on Earth, the oldest is approximately 4 billion years old. We can know about the age of that one by looking at the microscopic crystals inside this rock. At that time, it was suggested that there was actually liquid water on Earth at that time. So very early, we have liquid water. So I think this is an animation of the...
What Earth looked like during its first 500 million years is unknown, as we have not found any rocks older than roughly 3.8 billion years. But scientists think our planet was constantly hit by a rain of asteroids that melted the surface and boiled the oceans. A recent study by geologists at the Southwest Research Institute in Boulder, Colorado, has attempted to show what really happened during this volatile Hadean period as it is known. The evidence of all the asteroid impacts was covered up over time by erosion and plate tectonics. So to study the conditions of early Earth, scientists looked to the moon. They analyzed the frequency of different size craters on the surface of the moon to measure when asteroids of different shapes and sizes made impact. Using this information, they created a computer simulation of the size and frequency of asteroids that may have impacted early Earth, including several more than 600 miles wide. Dr. Simone Marchi of the Southwest Research Institute, who worked on the study, is quoted as saying, "We found that the magma oceans were likely to be regional events, so at any given time, there were some locations that were calm. That means liquid water could have existed in one place or another throughout the 500 million years of the Hadean period. Though it's also possible that life existed at that time, it would have had to survive some harsh conditions."
Okay, after talking about our Earth, we need to talk about the moon, our moon. And the evidence suggests that the moon is formed a bit later, at about 4.48 million years, or 70 to 100 million years after the formation of our solar system, that is formation of Earth. It is a very large size rock, about the size of Mars, hitting on Earth. Because of the size of that Mars is so large, therefore it melted part of the Earth's surface, and the melted debris flung into the Earth's neighborhood. But again, this is being attracted by the Earth, and therefore they can't go away very far, and therefore it surround around the Earth, and then eventually also attract towards each other and form our moon. So that is the theory of the formation of the moon. First, the moon density is a bit lighter than our Earth. That means when that large rock that hits Earth at that time, Earth has already get most of its heavy element into the core, and therefore it can only melt the outer surface, and therefore it is lighter than Earth itself. The moon is about 3.3 times the mass of water, where density of water, whereas we are 5.5. So a lot of our heavy elements is actually at that time is already have been located in our core, in the middle. And secondly, there's no water on the moon. There are several reasons for that one. One of the probable reasons may be the asteroids which hit on the moon will cause so much heat that the water becomes evaporated, and because the moon does not have sufficient gravity and cannot hold it, and therefore the water get ejected out of the moon. That might be one possibility. The third is we have the same oxygen isotope, but we know that on the surface of the moon there's no atmosphere, and because there's no atmosphere, that means it does not have the weather patterns which we observe on Earth, and therefore the moon doesn't have weathering. Because the moon doesn't have weathering, therefore we can observe the craters much easier than on Earth here. On Earth here, we have all the weathering, the weather driven by the atmosphere, driven by the water, driven by the volcanic activity, etc., and therefore all the craters on Earth has been weathered away, whereas the moon surface preserved its look because there's no weathering. Again, that might be because it doesn't have sufficient gravity to hold an atmosphere. But for the little oxygen that's available from the moon, we find that it have the same signature as the oxygen on Earth, so they probably is part of us. This is the so-called giant impact hypothesis. We assume that the moon is formed by a rock at the size of Mars, which strike the Earth at an angle. That a collision release a lot of energy, vaporizing some of the Earth's outer layer, and melt both part of Earth and obviously melted the rock itself. A portion of that mantle material, where it is hit on Earth, get ejected into the atmosphere near ejected out away from Earth, and that eventually form the moon. The moon and Earth is tidal lock. That means one of the most easy to observe feature of this tidal locking is that we always see the same side, same face of the moon. I think that I have a video here to show you what is a tidal lock. Oh, sorry, that one is about the formation of the rock. This one is the
In 1959, the Soviet spacecraft Luna 3 beamed back images of something Earthlings had never before seen, the far side of the moon. We always see the same old side of the moon because the moon rotates exactly once on its axis each time it orbits Earth. If it weren't spinning at all, we'd get at least one 360-degree view of its surface with each lap. If it were spinning twice as fast, we'd also see the moon's entire surface more than once per orbit. But instead, our moon's motions, like the spin and orbit of most other moons in our solar system, are remarkably in perfect sync. This wasn't always the case. Our best guess is that our own moon formed due to a massive asteroid impact, and its initial spin and dizzying 10-hour orbit were almost certainly not in sync with each other, though we don't know which was faster. At such close range, Earth's gravity deformed the moon into a slight oval, with one of its bulges facing Earth. Those bulges quickly swung out of alignment thanks to the moon's asynchronous spin and orbit, but Earth's gravity continually squeezed them back again. What's more, this gravitational tugging would have influenced the moon's rotation rate. If it was spinning more than once per orbit, Earth would pull at a slight angle against the moon's direction of rotation, slowing its spin. If the moon was spinning less than once per orbit, Earth would have pulled the other way, speeding its rotation. Whatever the case, it took just 1,000 years for the Earth's pull to adjust the moon's spin enough that one rotation of the moon corresponded to one trip around the Earth, leaving one side forever locked facing away. We do end up seeing some of that far side because the moon's elliptical orbit gives us peaks beyond its average eastern and western horizons, and its tilted axis causes moon seasons, revealing more of the lunar north or south poles. But those glimpses only add up to an extra 9%, leaving 41% of the moon hidden from Earth. Satellites, starting with Luna 3, have allowed us to map the rest, but it's safe to say that our relationship with the moon is still pretty one-sided. I'd like to say a big thanks to
Okay, so the video explained what is why Earth and Moon have a tidal lock. So because if the moon because the Earth and Moon are together, and therefore the Moon is not exactly sphere, it's slightly elliptical. That slight ellipse, of course, is exaggerated in the animation, will provide the pull to make sure Moon and Earth have the same rotation. So for the Moon, it rotates around us in 1 month, approximately 28 days something, and that means on the surface of Moon, the 1 day is 30 something days on Earth, and is 1 year around us is also 20 something. Is basically say is 1 day is almost the same as 1 year. So that's called tidal lock. And the other thing is, you want to study the beginning early state of the Earth. We said there is a heavy bombardment period. There's a lot of other things falling onto Earth. We must remember Moon is smaller than Earth, and therefore its gravitational force is smaller. Its gravitational attraction is smaller than the gravitational attraction of Earth. And therefore, if there are so many bombardments on the Earth, on the Moon, there must be more on Earth. So we can imagine at that time there's a lot of falling rocks from walk over onto our Earth's surface. So the surface of the Moon is a very good example of the kind of bombardment Earth experienced in the early days. After the birth of Moon, the Earth's surface slowly cooled, and for that one, our Earth's surface remained alien to modern life for at least 700 million years. At that time, there will be a lot of gases emitting out of our inner materials. Most of them will be carbon dioxide, nitrogen, water vapor, and so forth. But it won't have any molecular oxygen. Because of no molecular oxygen, and many of them are carbon dioxide. So the Moon at our Earth's surface will be much hotter than today. But eventually, the Earth's surface still continue to drop its temperature because the surface is a continental crust is formed on the Earth's surface, and then the water becomes condensed into lakes, and then become sea, and then become ocean, and cover about 70% of our Earth's surface. By then, the Earth temperature will be dropping much quicker than before. Initially, when there's a lot of bombardments, all these things hit onto Earth will give Earth the kind of energy, keeping its temperature high. But as the bombardment slow down, then its temperature rise will be slow down and even started cooling. When it started cooling, then it will continue to cool. Initially, we will have a very short-lived oceans, because whenever the oceans form, and then if there's another rock or something hit on it, and then it will evaporate, and then the oceans becomes steam and go to the atmosphere and blow away by the solar wind. So we guess that our atmosphere have changed a couple of times. There is a theory called late heavy bombardment. The late heavy bombardment hypothesis said that the bombardment events last approximately occurred, well, put it other way, last about 400 million years. So about 4.1 to 3.1 billion years ago, there is a period where there is a disproportionately large number of asteroids hitting the inner solar system. The evidence is brought back from the rocks on the Moon. So we can date the rocks on the Moon and find that all this rock seems to melt in a rather narrow narrow interval of time. So during that period, there must be a lot of bombardments melting the moon's rock, and then solidify again, melting, solidify, melting, solidify, and then by looking at when the rocks was last melted and when it solidified, we can find out the interval of time when there is a lot of bombardment. And it seems that at the moment, the evidence show that there is a heavy bombardment period 4.1 billion years to 3.8 billion years ago. So between that time, it seems that there's a lot of smaller particles falling onto Earth. I think we can understand it in a way that initially when the planets are formed, it will be crumbling larger rocks, larger derbies together. So during that process, it is the formation process. Whereas the smaller particles, smaller rocks, will be still scattering around without being clumped together. After the big ones are formed, they now have a gravity, and therefore you'll be able to attract the smaller ones, and eventually the smaller ones will all be gone and will have been attracted. So in between the formation and the smaller derbies are all gone, there will be a period, which period is what we refer to as the late bombardment period here. So it's probably after the lunar formation and before the Earth settled into a more stable environment. There are several criticisms of this hypothesis. Two main ones. The first one is the cluster of impact ages could be an artifact of sampling error, because when we look at the moon, we are looking at one side. We have it until lately there was no landing on the far side of the moon. China was the first country to land a spacecraft on the far side of the moon. What we have is only spacecraft spinning around the moon to have a look, but that we haven't anytime land anything on it, and therefore we haven't collected any rocks on the far side of the moon, and therefore we don't know. So that is one possibility because of the sampling error. The second is again the similar thing. The lack of impact rocks older than 4.1 only means that we haven't found them. If we found them, we may have to adjust this theory. What is the geographical consequences on Earth here? If the moon have a late bombardment period, so would Earth. At that time, we are now looking at the kind of crater that's left on Earth. If the crater is large enough, it will take a long time to weather. So we should be able to see a little bit of the what is left behind from the crater. From that, we can study what is the size. So there are a number of observations saying that 22,000 or more impact craters will have a diameter bigger than 20 kilometers. About 40 will have a diameter bigger than 1,000 kilometers, and only several with a diameter bigger than 5,000. So that would be the estimate. Another thing is about when Earth have a solid surface. Before this late embankment theory, the geologists assume Earth will be melting without a solid surface until about 3.8 billion years ago. But now the data is being challenged. So we don't know. I'm not a geologist, so I will just leave it like that here. Okay, the oldest rock. What's the oldest rock? But we are looking at two kinds of rock here. One is the rocks which is original to Earth, and the other is the rocks which come from outer space and arrive on Earth and then collected by us. So there are two kinds of rock we are talking about here. The way to distinguish it, I don't know. I'm not a geologist, but somehow the scientists will be able to figure out whether a rock picked up on Earth's surface is that one of the rock original to Earth or it has come from outer space. In 1999, the oldest rock is discovered. It is about 4.031 billion years old. It is discovered in Canada. Another area which you might find very old rock is Australia here. So there are three geological areas which our surface has not been turned over by the tectonic effects. One is Canada, another one is Australia, and another one is Africa. We believe our continent is very old. That means it haven't gone underneath another continent and get melted. Because of that, we might be able to find very old rock in these three areas. The oldest at the moment is found in Canada. It looks like this. It looks to me like a sedimental rock, but again, I'm not a geologist, so I can't say why it is look like that. But that is one of the rock that is supposed to be very, very old. As I said, there are two kinds of rocks. One is original to Earth. Another one is coming from outer space. One of the meteorites dated to be 7 billion years old. So that means we should have been triggered by something 7 billion years ago, a supernova. Only a supernova can produce rocks. So probably 7 billion years ago, somewhere near Earth, there's a supernova, which might trigger the later supernova, which initiate the formation of Earth. Okay, and that's the presentation. Question time. I see some of you have your mic turned off, so you would like to ask a question. Please unmute yourself. Yep. Any question?
I can't think of any, Albert, but it's interesting again, and we can see how it comes into play, how everything fits together. All the facts are there, agreed as facts, and then some of that last bit where there's some contention.
Yeah, I think this is this. That's why I say the big history is a scientific story about our origin. It started simple. Big Bang is just energy, and then it produced very simple elements, hydrogen, helium, a little bit of lithium. But because of very slight variation in its density, and therefore gravity kicks in. Gravity kicks in, causing the denser regions to attract more gas, and therefore it started lighting up, become stars. The stars go through its life cycle, and then some of them, during that life cycle, it formed other elements by nuclear fusion from hydrogen, helium, carbon, oxygen, until up to about iron. Of course, there will be some higher than iron as well, but that will be minimum. But at the last explosion during a supernova, then more of these elements heavier than iron is formed. And then this supernova trigger other regions to collapse, to become a star, like our sun. And because of that, near the sun, there will be other heavier elements. similar to our inner planets. And these inner planets, during its formation, also go through its evolution. So we are now just covered at the early Earth at the moment. So we know that Earth is unique in one way because it is hit by another rock which is the size of a small planet, and it becomes our moon. So relatively, we have a very heavy moon in the inner solar system. In the outer planets, yes, there are moons which is much bigger than Earth, but in the inner planets, our moon is pretty large, and our moon is also tidally locked to us because it was formed by a rock hitting us first and then get ejected and then swung into our orbit, the moon's orbit, and then collected together to form the moon. Being smaller than us is also given another possibility of looking at what happened at the early stage, because it doesn't hold a hold gas. Therefore, it doesn't have weathering. Without weathering, that means we should be able to see its original form. So by looking at the moon, we see all the craters. So we understand, at the early stage, we also must have a lot of craters. But because of weathering, all that crater is now being weathered out, so we don't see it. And so that is a very simple way of starting. And then, of course, we later on we will talk about the origin of life, how life started. This is a big mystery, how life started. But once life started, then its evolution path is pretty clear. We can follow through the evolution path until it comes to human. And then from there onwards, we will talk about the evolution of human, how we eventually come to the state we are now. And then we'll look into our current society.
Why do they call it tidal locking?
It's tidal locking. Because the moon and us is tidal locked together in the sense that our tide depends on moon as well as the sun. And the moon actually have a larger effect on our tide than moon. Now, on Earth, we have water. The moon is attracting the water towards it. So when the moon is on that side, the water is being attracted on this side of the Earth. When the moon is on the other side of Earth, it will attract it to the other side. So the water is being pulled by the moon, and when the water, our sea water being up and down, we call it tidal. So it's and therefore we call it tidal locking, because the moon affects our tide, and the tide is caused by the moon's attraction. But the moon's attraction also causes it to.
But they said it was the misshapen political shape that causes the locking.
Yeah, the shape of the moon.
One face. So what's that got to do with tide? I can't see any connection with it.
Yeah, the shape of the moon caused the moon to get in sync with us, so that it's always facing us the same direction.
Sure, I get that bit.
But
I
then
can't see why that's called tidal locking.
Well, and then at the same time, the moon, now the Earth have sufficient angular momentum to rotate at its own rotational speed. Earth is not tidally locked to moon. Moon is tidally locked to Earth. Now there are some situations when both of them are tidally locked together. That means Earth will always see the moon on the same side, and the moon will always see Earth on the same side. So they will be tidal locked together. But in our case, we rotate faster. Moon will travel slower, but moon will always look toward us. We always saw moon on the same side.
But say you had two objects that notionally are called tidal locking, have no water on them, whatever, you could have a situation where two objects face each other the same face to each other all the time, but no water involved in it. But would that still be called tidal locking?
Yeah, that will still be called tidal locking. Tidal locking actually is a term borrowed from tide, and then becomes its meaning is that they will face each other on the same time.
Oh,
So when the moon is tidal locked to
so-
us, then we see the moon
okay.
always the same side. But there are other planet systems in which both of them are tidal locked together. That
Okay,
means
so the tide means tied together, nothing to do with tides in
no,
water.
nothing. But of course,
Okay. All right,
I-
I'm with it now. Sorry.
it's a terminology problem. Sorry,
Yeah,
we misunderstood the
yeah.
problem.
I'm sure. Yeah.
Thank you for the question.
Thanks.
Yes.
Yes.
Albert, I could see the possibility here, or the likelihood, that where different objects have impacted the Earth in the past, that's where we get a concentration of a certain type of mineral in one part of the world and a different type of concentration in another part, where there's oil countries, there's
Yeah.
Australian mines with iron ore, etc., and others have got copper and others have got some other attribute. I could see that. The thing I was going to ask you is, you said there's no weathering on the moon. Is that because the moon has no atmosphere?
Yeah.
Whereas we have, is it as simple as that or more complicated?
As simple as that.
Yep.
Because weathering is a atmospheric effect. So without atmosphere, we won't have weathering. So the moon doesn't have a thick enough layer of air to cause weathering, whereas our layer of air. But if you look at the actual layer, we're talking about a few kilometers thick of our atmosphere, compared with Earth, which is, I think, is 2,000 something kilometers in diameter. So the atmosphere is actually very thin, very, very thin. But to us, such a small animal, that becomes thick. But the atmosphere is actually pretty thin compared with the surface of with the Earth itself. Earth is at least several thousand kilometers in diameter. Our atmosphere is at most one of several kilometers. So
Yes. On another matter of general comment that I saw during the week, on not the tidal locking, but the tides, the water tides, the highest one I heard of during the week, one in Canada, the figure was 70. It must have been 70 feet. And it was a very long inlet, something like 160 kilometres long, and it narrowed in. And when the tide was starting to come back out, the new tide was coming in, and then you had a
collision.
doubling up, if you like. And where there was weathering on the side of this bay or inlet, you had very weird shapes as we get elsewhere, and very remarkable, and thinner at the bottom than the top, and then at some stage they would collapse, but quite remarkable. So it was somewhere east of Quebec, probably due east, probably 100 to 200 kilometres east of Quebec. Quite interesting phenomena.
Yeah, when later on when we talk about weathering on Earth, I probably would try to find what you have described, and then get a video. I also know of another example in a place in China, and then it said when the tides come in, in a straight line. It's again very spectacular. Again, it's the same thing. One tide coming in, one tide coming out, they collided and then cause it to form into a very strange behavior. That's quite interesting. So when I talk about the weathering, etc., I probably will be thinking about these different tidal phenomena. Yeah. Yes.
Is that the one is called the Qian Tang?
Yeah, Qin Gong, yes.
A couple days ago, I just seen on the TV that Universal is actually moving. I seen the picture that the Universal that's one is on the one curve, and then the whole entire thing is moving up and coming down. So what do you think on that?
I don't know. I haven't seen that. Can you
Yeah.
send me a link so that I have a look? And then
I watched it on the TV. It's
Oh.
just passing by and it showed up, and I couldn't know his name.
which channel?
Normally it's channel 7.
About what time? When?
Just about 3 or 4 o'clock.
Okay, I will
Yeah.
try to see whether I can find it and then have a look. If I can, then I probably might have a few comments. Otherwise, I will just have to leave it like that.
Yeah, okay, it's all right because I seen it on the screen, on the TV screen.
Yeah.
Yeah.
And-
Sam, I didn't quite understand what we're talking about. What was it again, please?
He talked about the. I let Sam talk about that. Yeah.
Yeah.
I just watched on the TV, and that's I seen the TV the screen showing the Universal's what is it the nebula,
Oh, Nebula, yes.
which have been moving, so moving moving up and moving down. So yeah, that is one which I think is a couple of days ago. I think I'm not so sure.
Yeah. So I will
Yeah.
have to follow that up in order to know what you are talking about.
Okay.
Okay.
And talking about the tides, actually the moons has no air at all.
Yeah.
And you have been saying that if there is any very, very tiny atmosphere, supposing that is correct,
No,
then-
now if there is any atmosphere, the atmosphere will be very, very thin, because the moon doesn't have sufficient gravity to hold the gas.
that's
The
right.
moon, you will be experiencing the same solar wind as we experience, but it has such a smaller mass, it cannot hold the atmosphere.
Mhm.
So if there's atmosphere, it will be very little and probably almost none, because what we see on the moon is we see all the craters at the moment. So these craters we're talking about 4 billion years ago. So it's still there. So that means it has almost no weathering. So
Right.
that is quite different from some of the other giants. There's a lot of weather in some giants, but not our moon.
Because as a Chang'e number 2,
Mm.
which is still sit on the behind the moon.
Yeah.
And it has been sleeping for the last 6 months already. No, within the last 6 months have been sleeping and awakened for the 3 times.
Yeah.
And
It needs energy, so it will. Now there are two issues with on the other side of the moon. When it's on the other side of the moon, that means it cannot communicate with us. The moon block any direct signal. So in order for that aircraft on the other side of the moon to communicate with us, we need a satellite moving around the moon. And then it will send the signal to the satellite, and the satellite relay that signal back to us in order for us to be able to get the signal. So I don't know what is the orbit of that satellite. If the orbit is perpendicular to moon's orbit around us, then probably that won't work. So there are two issues here. One is the landing craft on the far side of the moon need energy, so it can only recharge it using solar panels. So it is only when the moon other side is facing the sun, then it get recharged, and when it get recharged, it can start working. And then we also need a satellite something in the right place for it to communicate and let the satellite send the information back to us. So I don't know the details about that, and I don't know what the reason why you have to sleep and wake up. But energy is one issue. The other issue is actually commands. How can we send command to that aircraft on the other side of the moon, which theoretically we can never see because it's on the other side of the moon. So we need something as a relay to pass the commands to that and let that send the information back. And again, that relay, how that works, I don't know. It must have some kind of relay orbiting somewhere so that its signal can be sent to the relay and the relay back to us.
That's why you're quite correct, because if it's only awakened for the one time, and it might be just to get the chance.
Yeah.
But it is already repeated 3 times already, and still keep going on, and still can.
It's still working.
Some rock or some dust over there.
Yeah, it's still doing some experiments, but it's limited by the energy on board, how much energy it has. And obviously, again, its other issue is communication back to us.
Yep. Thank you.
Thank you. Okay, if there's no more questions, we'll end this one and
One
then.
quick one.
Yep. Go ahead, Gilbert.
I just want to clear something in my head. The sun is in the center of our universe, isn't it?
No, the sun is not the center of the universe. No, nor is the center of Milky Way the center of the universe. There is no center. You can treat any point in the universe as the center, and then look at it from your own perspective. But that is not the actual center.
Okay.
Yep.
Again,
Clear. Thank you.
talking about that, it's Milky Way, and it also shows that we are not the center, and it is kind of they're pointing Earth on the certain area in the lower section. And how do we know that we are on the lower section?
That is a very good question. I think I will need a whole lesson to answer that one. So leave it out like that. I will answer it a little bit later on. Okay? That's a very good question.
Yeah.
Okay.
I'll see you in 5 minutes.
Yep. See you in about 5 minutes on China Today. Thank you.
Thank you.
Thank you.
Thank
Bye.
you.
See you
Bye.
later.
Bye.
Yeah. Thank you.